Everyone, welcome to the fourth day of online international workshop on machine learning applications to images, IoT and wireless sensor networks. Today we have Dr. Shivram Dubey from IIIT Sri City. Dr. Dubey works extensively in the area of computer vision, image processing and related fields. Dr. Shivram Dubey, in my personal opinion, is a great friend of mine, and he has also extensively worked in this area and has some of the very good, very, I would say, the best publications in the area. He is one of the leading researchers whom I am friends with, and I'm very proud to say that I know Dr. Shivram Dubey as a friend, as a colleague, and as a fellow researcher. So welcome, sir. Uh, just to introduce you about the workshop, I would I'll tell you something about the workshop, what the workshop is about, and this workshop is being hosted by IIIT Lucknow, and it is in collaboration with University of Essex. The workshop is funded by GCRF, Global Challenges for Research Fund, and this is a 5-day workshop. Tomorrow we are concluding these sessions. Tomorrow will be the last day of the workshop. So without without making any more introductions and delaying the entire session, I would request Dr. Shivram Dubey to start this session. And sir, we will be recording these sessions so that we can post it on our YouTube channel as well. So thank you so much, sir, and you may start, sir. Over to you, sir.
Okay, thank you very much, Vishal, for introducing. So first of all, let me check just with the audio. So audio is fine, or is there any issue with
Yes,
my audio?
the audio is clear, sir. It is perfect.
Okay, fine. So then I can switch off this video mode and I can only continue audio mode so that there should not be any problem.
Yes, sir.
Our video is required?
No, sir. Whatever is comfortable for you, that is okay.
Okay, fine. Okay, so a very good morning to everyone, and welcome to this workshop on online international workshop on machine learning applications to images, IoT, wireless sensor networks. And myself, as Vishal already introduced, that Dr. Shivram Dubey, working in IIIT Sri City. Before going to the topic, I will just try to just introduce quickly that what is IIIT Sri City. So IIIT Sri City is one of the IIIT that is set up by MHRD under PPP model, that is public-private partnership. So this is very similar to IIIT Lucknow. And it is actually it is located in Andhra Pradesh, which is very close to Chennai. Even it is in Andhra Pradesh, but Chennai is just 60 or 70 kilometers from here. Instead of basically this is on the border of Chennai and this Andhra Pradesh, on this highway from Chennai to Kolkata. That is highway that is actually this coastal area. Regarding programs here, so we also have the programs like BTech, MTech, PhD, and in computer science as well as in electronics and communication departments. But this year actually we are starting this master's program in AI ML. So if any one of you would be interested, you can check out this IIIT Sri City website, and still this date is still there. 31st July is the last day to apply. So if anyone is interested, you may have a look, or even you can also share with anyone else who might be interested. Similarly, we have the PhD programs. So PhD programs we also have in full-time as well as in part-time modes. And the major areas that we have in our computer science department, I belong to computer science department. This computer vision area is there, machine learning is there, deep learning is there, even algorithm area is also there, cryptography is there, cybersecurity is there. So we have almost all the areas which is roughly required for, let's say, computer science department. So if anyone of you maybe explore IIIT Sri City website, even faculty's profile, and here you can little bit explore about the place as well as institute, and if you are interested or any one of your colleagues are interested, you may share the same information. So that's it from this introduction side from my institute. Now coming to this lecture, in this lecture basically I am going to cover a journey from machine learning to deep learning. So what I will just this basic machine learning classifiers like linear classifier, support vector, and how to use in non-linear scenario as well as in multi-class scenario, and softmax classifier as well as then basically I will move to I will move slowly to neural networks. And what I will do, I will basically present a very consistent you can say framework. Even you will find that the same framework is going to be used for the deep learning also. It means that deep learning is basically evolved from the machine learning slowly in this manner. And if time permits, then I will also introduce a little bit about the convolutional neural network. And basically the application I'm going to focus on the classification problem. So now if you see here, suppose if you have two classes, just for example, here you can see, you can find some this rectangular boxes which is in the blue color and some circular this in red color. So now if you consider this one as this blue one as the example 1 are basically class 1, and the red one as the training example class 2. Now, suppose in a very simple scenario, this could be a point also in just a two-dimension world. Suppose if this is a point in two-dimension world, and if I want to say that, suppose if a new point is coming to you, let's say this is the test example. Suppose this is a new point coming to you, and you have to find out that okay, this new test sample should belong to this class 1 or it should belong to class 2. If you see visually, this is going to be a very simple problem. We can very simply say that this test example should belong to class blue. And why it should belong to class blue? Because obviously it is very closer to this majority of these training samples that we have for the blue classes. Okay, what could be the procedure here? How to find out? It's that we can say, let's say qualitatively. But suppose if we have to figure out in a quantitative manner, then how we can do it? That is also very simple. What we can do, then we can find out that okay, let's find out the distance from each of the training samples to the test sample, and let's pick one that particular training samples from which this test example is, let's say, the closest one, and whatever is the class of that closest training sample, the same class we can say for this test example. So that's how actually we can find out. And now after computing the distance, we can say that now because this is very closest to this particular sample, and this sample is belonging to the training example class 1, so this test example should also belong to the class example 1. Now, if you see, the same thing can happen even for the data that is more than, let's say, the dimensionality is more than 2. Even it can be an n-dimensional data also. You can think like this, that this is a point, but this point is represented in n-dimensional world, where a point is basically represented by n number of coordinates. So now, now, if you see, if you want to write in a function form, then we can say that this fx is equals to nothing but here label of the training example nearest to x. So what is x here? X is nothing but the test example, and what is f? F is a function, and how this function is working, that function is basically computing the closest, let's say, the sample in the training example, and just transferring the class label from that closest label to this test example. And even we can extend this nearest neighbor to the k nearest neighbor. In k nearest neighbor, what will happen, instead of finding only the, let's say, the closest example, we will find, let's say, k number of closest example, and then we will take the majority outing out of those k number of this closest examples. So for example, here you can see, suppose if k is equals to 5, and let's say if we have a 2-class classification problem, and suppose if x is the middle one for which we want to do the let's say classification, that it should belong to the red class, or here black class. And suppose if we is there some noise? Okay, so now suppose if we find out the 5 number of nearest neighbors, so let's say these are 5 nearest neighbors. Out of these 5s, if you see, 2 are from the red category and 3 are from the black category. So we can say basically this x is going to belong to the black category, because that is going to have the majority in this 5 number of nearest neighbors. So that's how actually we can have this. And now if you see here, what could be the implications here are basically if you want to visualize that what is the effect of nearest neighbor. So here you can see, suppose if this is the data distribution that is given, and now suppose if we want to consider each and every point as a test case, then in which class the test case should belong. So the middle one is basically the output of just one classifier, means by considering the value of k as 1. Whereas the last one is basically the value of k is equals to 5, so 5NN classifier. So here you can see, even in 5NN classifier, you can find that, let's say, some of the basically areas which is white. White means that this is ambiguous area. It means that, let's say, suppose we have here three classes, red, green, and blue. Now, what will happen? Suppose if we are going to have, let's say, out of 5 neighbors, 2 are from the red category, 2 are from the green category, and 1 is from the blue category. Then now more than one category is having the same number of nearest neighbors. So we cannot decide. So that is going to give us the ambiguous, let's say, classification. So this white is represented as ambiguous. But apart from that, if you see what is basic difference here, if we are using 5NN classifier, then this is going to be robust to outliers. Now, what is the meaning of robust to outliers here? So if you see in this particular example here, that is the NN classifier. So in NN classifier, if you see, there is one small, basically island you can find green category, but actually that is outlier, because if you see those points are coming in between the red category. So that should generally not happen. If it is happening, then this is very high probability that this is actually outlier. But such outliers can be basically we can get rid of such classifiers, such kind of outliers, if we are going to use more than one number of let's say nearest neighbors. So that's what is the interpretation of this NN classifier as well as KNN classifier. This is now one question comes that suppose if we are using KNN classifier, then what should be the value of K? So that is one of the question, because K is here a hyperparameter. Now how to use, how to find out the value of hyperparameter? Then obviously there is no hard and fast rule for this, but generally people use odd numbers like 3, 5, 7, 9 like that. And in fact, this is just one empirical observation over one standard dataset, which is called CFAR10 dataset. So CFAR10 is a dataset that has 10 classes, and each classes have basically 10,000, 5,000 training images and 1,000 testing images. So total dataset size is actually 60,000 number of images. These are object categories like dog, cat. So these type of objects are there in this particular dataset. So now here you can see in this particular, for this particular dataset, after changing the values of K, it was discovered that K is equals to 7 is better for this particular dataset. Now, if you see K-nearest neighbor classifier, so first of all, this is non-parametric classifier. Why this is non-parametric? We have not involved any parameter that is going to be learned. We are not learning any parameter. K is one of the parameter, but actually that is not learnable parameter. So it is actually referred as a hyperparameter. What are the advantages here? Very fast at training time, because we don't have to do any training. Only we have training data. Everything has to be done at the testing time. We have to compute all the distances at the testing time only. So if in fact that is going to be one of the drawback also, because at the testing time it is going to be very time consuming. So suppose if you have, let's say, 1 lakh number of images in your training data, and now if you are getting one test data and you want to do the classification, then you have to basically find out the distance from this test data with respect to all of the training data, and that is going to be very time consuming process. It can work with any number of classes. So these are some of the advantages. And if you see the downside, then obviously we have to basically match with all of the training data. Then this is going to be very slow. And in fact, we have to store the training data always. Means if a new data is coming and you want to basically do the classification, you want to do the matching, or you want to find out the distance, then you have to memorize all the training data. And suppose if you have, let's say, very big data set, suppose if you have some million number of images, then it is going to take some let's say 50 GB or even 200 GB memory. That is also going to be very let's say inefficient to handle such kind of classification problem. So now if you see here, if we can extend this KNN classification a little bit to the linear classifier. Now what is the linear classifier here? So now earlier, if you see, we were thinking in terms of the computing the distance from the test data with respect to all of the training data. But now in the linear classification, now suppose if I say if you see this example that is on your screen right now, again the same example. Suppose if I say these are just point in a 2-dimension world, and now if I ask you to find out, can we find out a line that can basically separate these two distribution? So obviously visually, because this is actually a linearly separable data, so we can have a line in between this which can clearly separate this red class category from the blue category. In fact, you can see like this we can do this separation. Now if you see, suppose if this line is given to you, suppose if I give a line to you, and now if I give a point and if I ask you this point is above the line, or let's say right side of the line, or it is down, or let's say left side of the right line, then actually we can find out it very easily. How we can find out? So suppose if you have the equation of a line, and now if you are going to have, let's say, one point, what we have to do, let's just put these coordinates here in this particular line. If the value is 0, it means that that point is exactly on this line. But if the value is more than 0, it means that it is going to be somewhere at the right side or upside. If it is less than 0, then basically it is going to be left side. So that's how basically we can do the classification. So it means that suppose if we can have such equation of a line, then for any test case, what we have to do, we have to only find out that if you just use that particular point to solve this particular equation, then whatever values we are getting, if that value is positive, it means it is belonging to class 1, and if values is negative, it means it is belonging to class 2. But it seems very simple when we are talking about this particular two-dimensional scenario. What will happen in n-dimensional scenario? Suppose if these points are n-dimensional, basically these are, let's say, some feature vectors, n-dimensional points, then basically instead of this line, we can say we can have such a hyperplane. So hyperplane means a plane that we can think in terms of some n-dimensional world. In n-dimensional world, if you think of a plane, that you can refer as a hyperplane. So now suppose in n-dimensional world, if this is a hyperplane, then again it is going to be true. Again, the same thing is going to be true, that if you have a coordinate of an n-dimensional point, you just solve this line of hyperplane, this equation of hyperplane. If the value is positive, it means it is at the, let's say, one side. If it is negative, then it is at opposite side. So now again in mathematical form, we can write like this. So basically we are going to compute the sign of w dot x plus b. Now let's see what is this w dot x plus b. So w dot x is nothing, but this is going to be your equation of your hyperplane, or in fact w dot x plus b is the equation of your hyperplane, where this dot means here this is a dot product. So w means it is going to have, suppose if you have, if your data is n dimensional, then w is going to have the parameters, basically n number of parameters like w1, w2, w3. Then equation of your hyperplane will become w1 x1 plus w2 x2 plus w3 x3 plus w4 x4, like this. And ultimately this b is going to be a bias term here. So now suppose if you have, let's say, some point here, then you have the values of basically x1, x2 up to xn. And suppose if you already know the equation of this hyperplane, it means you also know that what is the value of w1, w2, w3, w4. And then in that case, and what is the value of b? Suppose if this is known, then if you are getting any x here, so because x is represented as a vector here, so basically it has n number of values, basically representing a point in n dimensional form. So now if you see here this w dot x plus b, now in fact we can also write in this matrix form here. Now in this particular example here, you see, suppose linear classifier here we just explained in terms of the two classes, but suppose if we have more than two classes, then what is going to happen? Then what is going to happen, we can have now w for each of the class. We can have one row of w for each of the class. Now if you see this w here, now what is the dimension of the w? That is going to be governed based on how many number of classes we have and what is the dimensionality of my data. Just for example here, in this particular image, suppose if we just stretch these pixels into a single column, and suppose after stretching into the single column, let's say we have 4 values. Obviously it is not realistic because you can see a lot of pixels are here, so this is just assumption. It is not going to have only 4 values. Actually it is going to have, let's suppose, n number of values, if n is the, let's say, number of features here. But just for example here I am considering 4, but it can be more than 4. So suppose if your data is a 4-dimensional data, it means you have 4 values here in your xi. You can see that xi is nothing but this is basically your data after doing some pre-processing. Now if this is your data, and suppose if you are trying to solve a problem for 3 classes, let's say cat, dog and sheep. Suppose if you have 3 classes, in that case, now what should be the dimensionality of the w? So the dimensionality of w is going to be 3 cross 4, where 3 is the number of row and 4 is the basically the 4 number of columns, and each row is going to represent the classifier for each of the classes. For example here in this particular example, the first row is representing the classifier for the cat category. The second row is representing the classifier for the dog category. The third row is representing classifier for the SIP category. And now question comes that, okay, then how we are choosing the number of rows? Then obviously number of rows equal to number of classes. Then how we are choosing the number of columns? Number of columns are nothing but number of columns are same as the number of features that we have in our data, or basically what is the dimensionality of my data. If I have 4-dimensional data, then here I am going to have, let's say, 4 number of columns. Suppose if we are going to have n-dimensional data, then I am going to have n number of columns. And now what is going to happen here? Basically, this is going to be just matrix multiplication, w into xi. So here you take the first row and then multiply, do the dot product with the xi, and then just do the summation here. Fine. This b is the bias term here, and then we are going to produce one score, and this score is going to say that what is the let's say likelihood, or basically what is the likelihood that this particular example or this particular input xi is going to belong to cat category. Or suppose if you see the second value that we are getting in our output, that is 437.9, how we got those values? So that value we are getting from the second row. So basically we are taking the second row and we are taking the input, we are taking the bias, and if we just do this computation, we will get this value. But and what does it mean? It means that this particular example xi, there is 437.9 class score. It means if the class score is higher, it means this particular example to in that class is higher. Similarly, the third row is going to give us the class score for the third class here. Then in this example, that is the SIP category. Yeah, but now if you see here from this class score, actually we can get to know that this particular example should be classified in which class. So now if you see in this particular example, this input image should be classified into the dog category, because the dog category, for dog category we are getting the highest score. But we know that this example is, let's say this example is not dog, let's say this is cat. It means that if this is cat, but if we are getting highest value for the dog, it means whatever is the value learned for the W and B is not correct at this point of time. So we need to change it. So first of all, how these values are initialized and how it is going to be changed, if we can figure out that if it is not working properly, that is going to be basically leading to the whole story of this machine learning as well as deep learning. So that we will discuss eventually, but at this point of time, just think about this, that somehow we got some value of W and now we have input, then we can produce a class score, and from class score we can figure out that this is performing well or not. If it is performing well, then that's fine. It means that whatever value of W, that parameters we have learned is okay. But if it is not performing well, then we need to change the value of W. And how we are going to change the value of W? In order to do that, different basically machine learning classification techniques comes into the picture. In fact, deep learning is also going to do the same task. So deep learning is going to use gradient descent in order to update the value of W and B. So again, writing in the mathematical form here. So now if you see, this is nothing but W multiplied with X plus B is going to give us the class score. And now what should be the dimensionality of W and B? That is going to be governed from the fact that how many number of classes we have and what is the dimensionality of our data. So if you see here, this is just visualization of the learned weight, means already training has been performed over CFAR10 dataset, and after training, so now suppose, let's say this this particular example, suppose in this particular example, suppose if we have n number of values, suppose if this is n dimensional data, then in each row also we are going to have n number of values in W. It means that, and each row is going to represent as a classifier for that particular class. So in fact, if we take that particular row of the already learned classifier, then we can visualize also that what actually it is basically looking for in the image. So here you can see this is the template that is after learning, that what it is looking for. So for example, here this plane category, if you see something is coming in the middle, car category, if you see something is coming as a Redis kind of a template. So basically it means that in that particular data set, most of the cars that is used for the training purpose might have the red color, majority of the classes. So that's why it is biased towards the red color. So like that, if you see, this is basically, it means that the classifier is trying to learn very similar characteristic of the type of the basically that particular object for which this classifier is trained for. So this is a bias trick. So bias trick is basically this bias, instead of outside we can have it inside also. Then what we can do, basically we can have one extra column as the bias, and then we can add one more value in our data as a 1. Then basically mathematically we are going to end up with the same value. So now if you see this linear classifier, so this linear classifier is actually root to, if you see, all other classifiers that is going to come. So basically this is a parameter classifier, as let's say contrast to the nearest neighbor classifier, which was non-parametric, because in linear in nearest neighbor classifier there was no parameter that we can learn, or we can change the value of that parameter. But here in linear classifier you can see this W and B are basically the parameters, and what should be the value of W and B, that is the actually the whole story here, that how to learn the value of W and B, from where to start and how to change the value such that we can get the optimal value of W and B, which can lead to better classification for our problem. This is very fast at the test time. Why it is very fast at the test time? Because at the test time we don't need the training data. What we need at the test time, we only need this W and B. If you have W and B, any example is coming, just you do let's say X is the example, then just you find out W dot X plus B. Whatever value you are getting, you are going to get the let's say N. If you are having C number of classes, you are going to get C number of values, and now out of C number of values, for which class you are going to have the highest value, that we can say this example is going to be classified to that particular class. So this is going to be very efficient at the time, at the test time. Yeah, but in fact, but that might be a little bit slow at the training time as compared to the nearest neighbor classifier, but that is not a problem. Say nowadays we can afford a longer training if it is going to give you very good result at the test time and very fast result at the test time. See, suppose if you can come up with such a classification technique, even it is going to take, let's say, 1 year for training, that's not a problem if it is going to give you guaranteed 100% classification with very fast after that. So that is not going to be an issue. And in fact, this linear classifier, one of the drawback is that it is only applied for the linearly separable data. What is the meaning of linearly separable data? If we have a training set, and that training set we can clearly divide using a hyperplane, then we can say this is the linearly separable data. But if we cannot divide, then that is not linearly separable data. That will become non-linear data, and non-linear data cannot be handled using linear classifier. And in practice, in real life, actually the data that generally we get for the such type of classification problems are non-linear in nature. So that's why theoretically this is a very good classifier, but obviously not going to perform very well if you are going to have a non-linear data. So this is just a comparison with the nearest neighbor classifier. So nearest neighbor versus linear classifier. This is just pros and cons. The same thing we already just discussed. Next classification technique is support vector machine, and in fact you would have seen let's say even some different perspective of support vector machine. Now what I am going to do, I am going to connect the support vector machine with the similar concept that we just learned using the linear classification technique. What I will say rather, that support vector machine is also basic version here, or vanilla version is nothing but is also a linear classifier. But how to learn the value of that hyperplane, for that it is going to use some let's say approach. And what is that approach that we see here quickly? So now if you see here again, we are going to have suppose two classes, and in a simple scenario, let's suppose these two classes are linearly separable. So downside you can say some classes that is in a different color, and upside another class examples that is in different color. Now if you see, we are talking about linear classifier. Suppose for this particular example, suppose if you have to find out a hyperplane that can basically segregate these two classes, what would be that hyperplane? So this can be one of the hyperplane. But now question comes, is it only the possible hyperplane, or can we have few more hyperplanes? And obviously we know that this is not going to be the only hyperplane, because we can come up with infinite number of such hyperplanes in between this. For example, I have drawn 4, but in fact we have infinite such number of hyperplanes which can clearly divide these two distribution into two classes. But now, if suppose if this is a scenario, then question comes that out of these infinite number of hyperplanes, hyperplane means what? This is basically classifier. Hyperplanes, which particular hyperplane we should consider? So now what support vector machine is saying, that support vector machine is saying that we should consider that particular hyperplane which can guarantee the maximum margin between these two distribution. Now let's see what is the meaning of this maximum margin. So now here, if you see here, suppose if we are going to have let's say if you just take these two hyperplanes, let's say this is one upper hyperplane and this is one lower hyperplane, and let's say the main hyperplane is going to be in between, which is going to be separate. So suppose if middle one is the hyperplane that we say, let's suppose say that this is the hyperplane that is going to give us the maximum margin between these two distributions. Now let's see what is the meaning of that maximum margin. So maximum margin means that let's find out a upper hyperplane which is parallel to this middle hyperplane but passing to the nearest data in, let's say, upper class, and the same thing is true for the down class also. So now you can see we are going to have two basically hyperplanes. One is upper hyperplane and one is the lower hyperplane, which is basically passing through the nearest data in these two distribution. And whatever is the data through which it is passing, that data is actually called the support vectors. And the distance between these two hyperplanes, upper and lower, is actually called the margin. Now what is the objective of support vector machine? The objective of support vector machine is to maximize the margin. It means it basically to maximize the distance between this upper hyperplane and lower hyperplane. So now let's see that how it is going to guarantee this maximization problem. And as I just told that the points are basically the samples which are actually exactly lying on these upper and lower hyperplanes are basically nothing but the support vectors. Those are termed as the support vectors. And again, we are going to use very similar concept that we just saw in the linear classifier. Now, suppose if the middle one is our hyperplane, and let's say the equation of that hyperplane is w dot x plus b is equal to 0, then what will be the equation of this upper hyperplane? Then the equation of upper hyperplane will be dot x plus b is equals to 1. And what will be the equation of this lower hyperplane? The equation of lower hyperplane will be w dot x plus b is equals to minus 1. So now what will happen? Suppose if we have any point, if we have any samples, let's say in the upper class, which is above the upper hyperplane, and if we just solve this equation of plane with that particular point, then our output must be greater than or equals to 1. And similarly, if any point which is below lower hyperplane, and if we just replace in our main hyperplane, that is w dot x b is equals to 0, then whatever value we will get, that value will be. Yeah, so now suppose if we say that this upper class is represented with 1 and this lower class is represented with minus 1, then basically if we just write this, what should be the constraint here, then constraint is going to be w dot xi plus b is greater than or equals to 1 for all the positive classes, and for all the negative class samples it is going to be w dot xi plus b less than or equals to minus 1. So it means that and for support vectors, w dot xi plus b is going to be either plus 1 for the upper hyperplane and minus 1 for the lower hyperplane. And now suppose if we have to find out that what should be this margin, how to compute the margin, then margin basically we can compute very easily. So suppose if we know these support vectors, what are those support vectors, then we can find out the perpendicular distance from the support vectors to this hyperplane which is in the middle. And how we can find out? We can basically just do, we can utilize this w dot x plus b divided by the norm of w. Basically that is going to give us the distance from upper hyperplane to the middle hyperplane, and similarly we can find out from the lower hyperplane to the middle hyperplane. Then basically the distance is going to be 2 times here. And now if you see w dot xi plus b, that is going to be 1, either plus 1 or minus 1, and because we are taking the absolute value, then it is going to be 1. And why it is going to be 1 or minus 1? Because these are for the support vectors, and if you see for support vectors, it is either plus 1 or minus 1. So that's why this upper term is going to become either plus 1 or minus 1, and absolute will become 1. And because we are going to do 2 times here, 1 once from the upper hyperplane to the middle and once from the lower to the middle. So that is, and this distance is going to be same. So that's why now margin is going to be nothing but 2 divided by norm of W. So that's what is the margin, and that's we want to maximize. So basically this is a maximization problem, and this maximization problem can be converted into a minimization problem. And how we can convert into a minimization problem? So instead of maximizing 2 divided by norm of W, basically we can minimize norm of W divided by 2. So both are going to be basically the same problem here. Instead of maximization, we can convert this problem into the minimization. And what is the constraint? So the constraint is when the class is positive, then W dot xi plus b should be also positive. When class is negative, means y is negative, then W dot xi plus b should be also negative, means either negative means less than even -1, because even it should be below or above the let's say above our lower hyperplanes. So in fact, it means that if you just do the multiplication, then it should be greater than or equals to 1 always. And now how to solve these particular optimization problems. So here I am not going to go in the detail because it is going to be a very let's say complex mathematical problem, but you can refer these particular let's say resources here if someone is interested to see that how this optimization problem is solved. And but this is the solution. What is the solution here? After solving this, we are getting this W, which is nothing but there is some learned weight, which is this alpha I, and this Y is nothing but the class label, and X is nothing but the support vectors. So this alpha is going to be 1 only for the support vectors, and for rest of the examples it is going to be 0. So now if you see here, it means that we have to only memorize the support vectors and what is the classes of the support vectors in order to do the testing at the test time. And at the test time, what we are going to do, basically, suppose if we are going to get X as the input, then we got the value of W. Now from the W, we can get the value of B. So now W dot X plus B that we have to solve, and W is already computed. That is this one. And this X is our input. Then this X is going to be the dot product with this whatever W we have got. So instead of doing the dot product with the W, what we can do basically here we can apply a bias a trick here. And what is that trick? Instead of doing this dot product from W to X, what we can do, we can have this alpha I and yi separately, and we can do directly the dot product from X to Xi. And why it is going to be meaningful basically? Because it is going to give us the concept for the nonlinear SVM. So what we can do in nonlinear SVM, this particular dot product that we are doing. So now, first of all, what is the meaning of nonlinear SVM here? Okay, so SVM for more than 2 classes, I will come to that in shortly. But let's first just have a look over the nonlinear SVM. So now if you see, suppose if we have this linearly separable data, so what we can do, we can have a hyperplane. And in fact, then SVM is also going to have the hyperplane here. But suppose if data is not linearly separable, basically non-linearly separable, in that particular case, one hyperplane is not going to work. Then what we have to do? Then basically we have to project our data in some higher order space. If we project our data in some higher order space, then it is going to be basically separable in higher order space. And how it is going to be separable in higher order space? Here you can see, suppose if we just project this data that is in the middle one into higher order space, that is the bottom one. Now you can see in the bottom one, actually we can have a hyperplane that can separate these 2 classes. The same thing is even generally done in nonlinear SVM also, where we can project the data into at the time of computation can directly apply, we can directly apply a trick, and we can use that nonlinear function at the time of this dot projecting the data into the nonlinear space, and it is going to if you see here kind of kernels are used. For example, here we can use a polynomial kernel that can be used to the kernel trick SVM that we discussed here. So we already framed that what is the objective. So objective is nothing but to minimize this norm of W divided by 2, and this is subject to this is our constraint. And if you see here, but this is for the separable data. What will happen if data is not separable? If data is not separable, then basically we are going to have one more constraint here, or one more error term here, and that error term is nothing but minimization of the classification mistake. Means so if we have the non-linearly separable data, then obviously there is going to be the mistake. If we are having the linear SVM, then obviously some of the samples are going to be misclassified. But then in that particular case, our aim should be to have the minimum classification mistake as possible. So for that, actually we are going to have this particular term. So max of 0 comma 1 minus yiw dot xi plus b. Now if you see here, what is going to happen? Suppose if you have a positive example and if it is correctly classified, so then what is going to happen? If it is let's say if y is positive and w dot xi plus b is also going to be positive, positive means more than 1, then yi into w dot xi plus b is going to be more than 1. It means that this 1 minus something more than 1 is going to be something which is negative. Then max of 0, something negative, is always going to be 0. It means there is no error, because positive class is classified into the positive class, no error. Suppose if negative class is classified into the negative class, again in that particular case also yi into w dot xi plus b is going to be greater than or is equals to 1. So again 1 minus something greater than or is equals to 1 is going to be something which is less than or is equals to 0. Then max of 0, something which is less than or is equals to 0, is always going to be 0. Then again there will not be any error. But suppose if misclassification is happening, let's say a positive class example is getting classified into a negative class. In that particular scenario, what will happen? So if yi is positive and w dot xi plus b is going to be basically, instead of greater than or equals to 1, suppose it is if less than or equals to minus 1. If this is less than or equals to minus 1, then yi into something less than or equals to 1 into something less than or equals to minus 1 is ultimately going to be less than or equals to minus 1. And 1 minus something less than or equals to minus 1 is basically going to be something, some positive value, max of 0, something positive value. And then basically we are going to have the classification error, because positive class got the classified into a negative class. Similarly, if negative class example getting classified into the positive class, again this negative term, we will get some negative values, negative and negative will become positive, ultimately we will get some positive value. So 0, max of 0 comma some positive value, we will have some error. So basically in case of non-separable data also, instead of we are going to have this norm of w divided by 2. Apart from that, we are also going to have the classification error as the objective function. This is just the visualization of the same thing here. So you can see some of the red examples are basically coming down of the hyperplane, and some of another class examples are even going up the hyperplane, and then this is going to give us the misclassification. And because if you see here, due to the nature of this classification objective function that we are using, max of 0 comma something, which is actually depicting kind of a Hinge function here. You can see the left side. So left side is showing that, okay, what should be the error value? What should be what is the error value that we are getting in different scenarios? So if let's say if correct class example are getting correctly classified, negative class example are getting correctly classified, then the error will be 0. So that's why if you see after 1 we are getting flat 0. But in another scenario, if it is crossing, if it is basically belonging to some other class, and in fact if it is too far from the hyperplane, then basically we are going to have even higher value for the error. And the nature of this error plot is kind of a hinge plot. So that's why support vector machine are also termed as a basically kind of a Hinge loss based function. So nonlinear SVM that we just discussed here. So this is some example that how this nonlinear basically SVM is working. So this is just example with a function. So the suppose if this is a function, then we can represent this function as a multiplication of this another function. Let's say that is phi, and we can find out that function. And ultimately, if you see that function is nothing but something which is related to a polynomial function. So we can have a lot of kernels here. Those are non-linear kernels. Basically non-linear, if we are having the non-linear kernels, it means that what is the effect these non-linear kernels are going to have? They are going to treat your data in some higher order space. And when it is going to treat your data in some higher order space, then there is a possibility that even non-linearly separable data can also be pushed towards linearly separable property. Now, again, if you see what is the pros and cons for this support vector machine. So pros, it is kernel based framework. So obviously we have the parameters to be learned here. Cons, it is going to be have the problem if we are going to apply for the multi-classes. So obviously, how to apply for the multi-classes? Either we can go for two classes and we can combine, or we can look for some other approaches like one versus others. Computation, obviously nonlinear SVMs are going to be very computationally complex. And as mentioned, this multi-class support vector machine, so we can represent support machine objective function, basically the hinge loss that we discussed, very similar to the two class support vector machine loss. So for example, here you can see that Li, so Li is nothing but the classification loss is equals to max of 0 comma Sj minus Syi plus there is some margin here. Now if you see what is this Sj and Syi, so Syi is nothing but whatever is the score that we are getting corresponding to the correct class. What is Sj? The score that we are getting corresponding to other classes. So that's why J is not equals to Yi here. So now actually in order to understand that how this multi-class support vector machine is working, it is better we can have one example, and through one example this is going to be more clear. So now I'm going to focus over this particular example, because the same example I am going to use for another classifier, which is the cross-entropy, which is actually heavily used in deep learning. So, but this is the basic building block even towards the cross-entropy objective function. So now if you see, this is again very similar example that we took earlier. So suppose if we have a 3-class classification problem. So it means that this W is going to represent basically classifier for 3 classes. The first row is for first class, second row is for second class, third row is for third class. And suppose this is the data that we have. Again, let's just for example, suppose if we have a 4-dimensional data, and let's say these are the bias term. So now suppose somehow we got these values of W and B. How we got the values of W and B at these particular times? So just for example, we can think of some initialization techniques. So suppose some initialization techniques, or maybe after some updates also, let's say these are values of W and B that we have at this point of time. So now with this W and B, suppose if we have to apply support vector machine, then what will be the loss? Loss is going to be used in order to change the value of W and B. Okay, now in order to compute the loss here, what we have to do, first we have to find out the class score. How to find out the class score? So each row is going to give us one class score. So first row is going to give us the class score, which is minus 2.85. How to find out that? Take the first row of W, do the dot product with this Xi, we will get one value, and just take the first value in this bias term 0.0, add it. So we'll get the output as minus 2.85. How we will get the output 0.86 for the second class? What we will do, 0.7 multiplied with minus 15 plus 0.2 multiplied with 22 plus 0.05 multiplied with minus 44 plus 0.16 multiplied with 56. After that plus 0.2, we will get the value 0.86. So it means that the class score for the second class is 0.86 for this particular example. For the third class, it is 0.28. So now the question comes, how we can compute the hinge loss? So how hinge loss is going to be computed? So hinge loss is going to be computed based on what is the class score for the class and what is the class score for other classes. Now, just for example, here you can see at the downside, suppose if this particular example is belonging to the last class. So yi equals to 2. So here labels of the classes are 0, 1, 2. So 0 is for the first class, it means the first row. 1 is for the second class, which is the second row. 2 is for the third class, which is the third row. So it means that this 0.28 is the class score for the correct class, and minus 2.85 and 0.86 is going to be class score for the other classes like class 0 and class 1. So now what we have to find out here, we have to find out that this particular class scores that is generated is working or is let's say fine or not. What is the meaning of fine? Fine means if we can get 0 loss, it means that this particular W need not require any update. But if we don't get 0 loss, it means that this W has to be changed such that next time it should give the 0 loss, or if next time the loss should be decreased. Yeah, so now let's see that how we can compute this hinge loss here. So what we are going to take, we will take the class score for the correct class and the class score for other classes one by one, and we will compute the losses, and then we will just sum up all those losses. So now let's consider the class score for the correct class, which is 0.28, and the class score for the first class, which is minus 2.85. So now let's see that what loss we can get it. So now again let's get the same equation. What was the equation? So here you can see the equation is nothing but max of 0 comma sj minus syi plus margin. So just for example, let's consider margin as 1, where sj is class score for other classes and syi is the class score for the correct class. So now when we are going to compute the loss with respect to the first class, then sj is going to become minus 2.85, that is class score for the first class, and syi is going to be 0.28 because this is the class score corresponding to the correct class. And now 1 is going to be margin. It means 0 comma minus 2.85 minus 0.28 plus 1. So now if you see this minus 2.85 minus 0.28 plus 1 is going to give us some negative value. Then max of 0 comma some negative value is going to be 0. So it means that what does it mean? It suppose if the loss with respect to a particular class is 0, it means that the class score for the correct class is much higher than the class score of that particular other class. Not just higher, even it is more than the margin. It is at least more as 1. So it means that 0.28 is more than minus 2.85 at least by 1. That's what is the meaning of this whole objective function. The same thing is going to be computed for the second with respect to second class also. Now we have to ensure that the class score for the correct class should be more than the class score for the second class at least by 1. If it is not, then actually some loss is going to be incurred. So, and that's what is happening here. You can see max of 0 comma sj. Now in this particular case sj is going to be 0.86, that is class score for other class, and this is the second class, minus class score for the correct class, which is 0.28 plus margin. So now 0.86 minus 0.28 plus 1 is going to give us 1.58, and max of 0 comma 1.58 is going to give us basically 1.58, and the loss for with respect to the first class is 0, but loss with respect to the second class is 1.58. Then the total hinge loss, basically SVM loss, is going to be 1.58. So that's what is going to be loss for the support vector machine. That's how actually support vector machine is used in a multi-class scenario. Fine. Where this loss is computed with this particular formula, that is max of 0 comma class score for other class minus class score for correct class plus margin term, and that is going to be sum over all other classes. Fine. So that's what is basically the formula to compute the SVM loss, or that is also termed as a hinge loss. So now if you see here, what could be the drawback here of hinge loss? One drawback of hinge loss could be, so just for example, suppose if I say that the class score for the second class that we have computed 0.86, suppose instead of 0.86, just for example, or suppose the class score for the correct class is not 0.28, in fact the correct class score for the correct class is 2.0, just for example. Suppose if class score for the correct class is 2.0, it means what? It means that the loss is going to be 0 for this particular example, because this example is belong to the third class, and the loss for the third class with respect to the first class is going to be 0 because that is much higher, and for this with respect to second also it is going to be 0 because 2.0 will be at least 2.0 is going to be greater than 0.866 at least by 1. So then total loss is going to be 0. So what is one of the problem with the support vector machine are this hinge loss. That's why this another classifier that I'm going to discuss shortly, cross-entropy, is actually preferred over the SVM. SVM stops learning after some time when this hinge loss will become 0. There is a possibility that when the class score for the correct class is going to be higher than all other class scores at least by 1, then loss is going to become 0. And as soon as loss becomes 0, your learning will stop. It means that now you cannot further improve your model. And that is one of the drawback of this Hinge loss. In order to get rid of this this problem of SVM, if you see in deep learning, majorly cross entropy loss is used, which is also termed as softmax classifier is used, and that's what we are going to discuss. So now let's see that what is the softmax classifier. So softmax classifier is going to compute the class score based on the concept of probability, and how it is going to take care, how it is going to utilize the probability, what it is going to do. Now, after getting the class scores, what it is going to do, it is going to project the class scores as e to the power. So basically the loss is minus log of, if you see, this is nothing but this e to the power syi divided by sum of e to the power sj over j, where j is basically for all the classes. This is going to be nothing but the computation of basically the normalized, basically the probability for the correct class, and then minus log of probability for the correct class is going to give us the basically loss for the softmax classifier. So now if you see how it is going to work here, so basically syi or sj is going to be the class scores, and that class scores can be any value. Then e to the power that is going to basically what this e to the power will do, this is going to this will increase the difference in the class scores. If some class score is higher, it will make it even more, and if it is if something is close to 0, then it will make even close to 0. And ultimately if we will do the normalization, so just this e to the power syi divided by the summation is basically going to be normalized such that everything should come in between 0 and 1. If everything is in between 0 and 1, it means what? Means if all the class scores are normalized in between 0 and 1 such that if you just add all the class score, then the summation is 1. It means that in this particular setup, that class score is nothing but the probability of that particular example to be classified for that in that particular class. So we can have the regularization term also, which is nothing but this just taking the norm of the W that can be used to do the regularization. Regularization term, I'm not going in deeper here for the regularization because that is another complete, let's say, aspect of this generalization. So now again, taking the same example here that I discussed for the Hinge loss. Now this upper one is the Hinge loss. Now let's see that how we can compute the cross entropy loss, or basically loss for softmax classifier using the same example. So now again, if you see, this class scores are same, minus 2.85, 0.86, 0.28. In this scenario also we have the same thing, 0.86, 0.28. So these are the class scores. Now how this cross entropy loss will be computed, what we will do, the first step, just find out the exponential of all these class scores. Now if you take the exponential of all these class scores, what is going to happen? Now if you see one of the exponential property, that whatever is the input, you are going to get the basically positive inputs here. So now what output you are going to get here? For this minus 2.85, you are going to get 0.058. And if for 0.86, something like 2.36, for 0.28, something like 1.3832. Means whatever is the negative value, for the negative value will be converted into the positive, but in the range of 0 and 1. And all the positive values will be more than 1. And in fact, that will be even much higher. So it means that if suppose if class score is negative, it means that there is a very small, very less probability that that particular example can be classified in that class. And that's what is doing this. That's what this exponential is doing, converting everything into the positive value. But for the negative value, the positive value that is generated will be very small, and it will be in between 0 and 1. And after getting the exponential, now if all the values are positive, then what we have to do, just take the summation of all the values and divide. And just do the normalization by dividing with the sum of all these values. So now this is after the normalization here, that is 0.016 for the class 1, 0.631 for the class 2, 0.353 for the class 3. So now what is going to happen here? Now our cross entropy loss is going to be minus log of probability for the correct class. And if you see this particular example, belonging to the last class or third class, now what is the probability for the third class, which is 0.353. So it means the cross entropy loss is going to be minus log of 0.353, which is going to give us a value like 1.04. So now what is going to happen here? So the one problem that we highlighted in SVM loss is that SVM loss can saturate after some time when loss becomes 0. And here we can argue in cross entropy loss that loss cannot become 0 until until the probability becomes 1 for the correct class. Here, if you see minus log of something, under which scenario minus log of something we will get as 0. So when minus log of 1, then only we can get it 0. It means that if the probability for correct classifier or for the correct class is 1, then only loss can become 0. It means that, and if suppose if the probability for the correct class is 1, it means that probability for other classes have to be 0. And that is very real, that is very, let's say, scenario which is very ideal, and it generally doesn't happen in practice. So it means that until you are getting some class score for other classes, you will be end up getting some loss for the using cross entropy loss as softness classifier. It means that your model will be always trying to basically learn and always trying to go towards the scenario where the basically probability for the correct class should become 1. Obviously, it cannot achieve that. It is very difficult to achieve, but it will always try to do that. And that's how this cross entropy loss is better than a support vector machine as in order to do the learning. Yeah, but also this particular nature of cross entropy loss brings another problem for these deep learning models, which is nothing but that is called the overfitting. Because if your model is always trying to basically make the correct classifier correct classification with let's say 100% probability, that is the aim of the classification, then after some time when learning is happening, after some time it is going to even overfit the data, because it is always trying to basically push towards the 100% probability for the correct classification. So that is another problem again, and there are a lot of techniques that is proposed in order to avoid such kind of overfitting. I'm not going deeper in that particular direction at this point of time. Yeah, so now if you see this particular discussion that we just discussed now, exactly same idea is going to be used by the deep learning models, are basically the starting of the deep learning models, which is basically the neural network. So now if you see, a neural network is also nothing but neural network is a set of some neurons. And now if you see, those are neurons, are artificial neurons, and those artificial neurons are nothing but, we can think that those artificial neurons are nothing but as is also a classifier, a simple classifier. So now what we will do, let's take just one neuron. Suppose if you have only one neuron, then one neuron can be basically termed as a perceptron. So now how this neuron is working in artificial neural network, if you just take one neuron, then one neuron is getting inputs, getting some inputs. Let's say if you are getting D inputs here, then it is having some weights for all these inputs, and then these inputs are getting multiplied with these weights, and then it is having a bias term, and then ultimately it is going to compute the sign of this W dot X plus B. So now if you see, I hope that most of you would be familiar with this particular diagram, which is basically this perceptron diagram, where what a neuron is doing, it is taking the input and doing the dot product with the weights and adding the bias, and then finding the sign. And if you see, the similar equation we have already seen for the linear classifier. For the linear classifier also, we did the same thing. We had some W, we had some X, we had a B, and we also we performed W dot X plus B. It means that in artificial neural network, basically the neuron which we have is also nothing but a simple linear classifier, fine, where it is taking some inputs, having some weights, just doing this dot product, but and adding the bias term, and ultimately we can say that a neuron or perceptron can work as a linear classifier. Okay, if it can work as a linear classifier, then how it is going to be basically updated. So what we can do here, basically, if you see, this is the update rule for this perceptron. So let's go one by one here. So for example, suppose if we have the training instance X with label Y, it means X is the input and Y is its label. We can focus over two class classification problem. Y is equals to 1 for class 1, Y is equals to -1 for another class. Now what we are computing sign of W dot X plus B. Plus B we can get rid of. We can assume that B is 0. That is up to us. We can have B, that is not going to have any much impact here. So now suppose the sign of W dot X plus B. Let's say if X is the positive example, means from the positive class, it means Y is equals to 1. and let's say y dash we are getting as the output of sine w dot x. Now, whatever is the value of y dash is either plus 1 or minus 1. If it is plus 1, then actually it is correctly classified. If it is minus 1, then it is misclassified. If it is plus 1, then there should not be any update in w. But if this is a misclassification, then w should be updated so that next time it should be correctly classified. And how W will be updated. So this is called the update rule, which is used in deep learning. Even we are starting from a basic neuron, but the same update rule is going to be used even in the deep learning also. That W, that is a parameter, is going to be updated like whatever is the old parameter plus some learning rate multiplied with here y minus y dash is basically going to give us the difference between the actual class and predicted class multiplied with x. Now, suppose if x is the input, training input, y is a positive class, its value is plus 1. Suppose if the predicted class value, that is y dash, is also plus 1, then what will be the change in w? Then y minus y dash will become 0. It means that if y minus y dash is become 0, then w is going to be same as the old w. There will not be any change. The same thing is true even if the example is from other class. Means if y is minus 1 and y dash predicted is also minus 1, it means that is correctly classified. Then again y minus y dash is going to give us 0. It means there will not be any change. Now, how it is going to take care if there is a misclassification? Just for example, suppose you have an input x and the class label y is plus 1, but your perceptron is doing the misclassification. It is giving the sign of w dot x as a minus 1. It means if y is plus 1 but predicted y is minus 1, means y dash is minus 1, then what is going to happen? Now y minus y dash, if y dash is minus 1, then y minus y dash is going to become some positive value. When it is going to become some positive value, now this w has to be updated. But now this w has to be updated in which direction? There should be w, the w should be increased or w should be decreased. So it should be increased or it should be decreased. It is going to be dependent upon the sign of x. Suppose if x is the positive, if x is a positive value, then w is going to be increased. And if w is going to be increased, then next time w dot x is going to be increased. And when next time w dot x is going to be increased, then there is a possibility that sign of w dot x will become positive next time. It means next time it can do the correct classification. If the value of x is negative, then w is going to be decreased. So it means that if x is negative and w is getting decreased, then w dot x next time there is a possibility that sign of w dot x will become positive. It means there is a possibility that next time it can lead to the correct classification. So that's how this update is going to happen for this one perceptron. This is the same thing explained here that just I discussed. So now again the same thing here, a single neuron or perceptron can be used as a binary softmax classifier that can classify into two classes. If sign is positive, then this is a class 1. If sign is negative, it is the class 0. And basically whatever we are getting the value can be treated as a probability here. So now this is just loose inspiration with the human neurons here. If you see human neurons is also having some let's say neurons which is getting the inputs from let's say other neurons and doing some computation, and there is something called some firing are basically the impulses that is actually sent to other neurons which is connected to this particular neuron. Obviously this is not very right way to compare the let's say human neurons with artificial neurons, but this is just a loose inspiration that this is also trying to mimic some behavior from the process point of view, not from the computation point of view, because exactly the input that is taken from other neurons, how it is processed inside a neuron, that is still the mystery. So but here we are actually using a simple dot product plus addition with some bias term. That's what we are using as, let's say, as a processing unit for a neuron. So now a neuron here is also getting the input either from direct input from let's say your data, or getting input from some other neurons. That is also possible if we are having more than one neuron in our network. And then it is doing this computation, that is whatever input you are getting, some weights are there, just doing the dot product of those, adding the bias term, and then passing this information to the other neurons. But before passing this information to the other neuron, there will be a firing. Firing means let's say how much information it should be passed or in which form it should be passed. So that is going to happen through an activation function. And if you see in the previous example here that we discussed, this activation function is nothing but is a sign function. Sign function is activation function. If something more than 0, just pass +1. If something less than 0, just pass -1. So this is a kind of a firing in between +1 and -1, and that is a very simple activation function that we can say binary activation function. Yeah, but nowadays there are very lot of activation functions have come into the picture. For example, ReLU is one of the activation function which is very highly used in deep learning area. And if time permits, we will also have a quick look over that. So now basically we can have a multi-layer neural network. So now multi-layer neural network means now we are going to have a lot of neurons or a lot of perceptrons now connected in a fashion. And how it is going to be connected? So these are, the first one is the input value. Here you can see there is the input layer. It means this is the input. Now this is the final output. So this is the perceptron that we have as a final neuron. Basically we can say that is giving us the final output. But now the input is not directly fed to this final neuron. In between, we have a hidden layer, and that hidden layer has 5 neurons here. And now what is going to happen? Have any neuron in any layer is going to be connected to the all inputs in its previous layer. It means that if you see any neuron that is there in the hidden layer is going to be connected with all the, let's say all the elements in the input layer. Similarly, a neuron in the output layer is connected with all the neurons that is in its just previous layer, which is the hidden layer. Connected means what? These will be, the output of these hidden layers will be treated as the input for the output neuron. And then there will be the weights. It will do the multiplication with dot product with the weights, and it will add the bias term, and ultimately it will pass the information to the next neuron, next layer. If there is no next layer, then this is going to be treated as the output. So this is just a typical interpretation of even more than one hidden layer. So now if you see, we have now 2 hidden layer here, hidden layer 1, hidden layer 2. So output of hidden layer 1 is passed to the hidden layer 2. Then this is again going to do the processing, and then it is again going to pass to the output layer. So now if you see the deep learning, so deep learning is nothing but now this, if you see this multi-layer neural network, in this particular case, we have only 2 hidden layers. Now, if we increase this number of layers, suppose if we go for 20 layers, 30 layers, 40 layers, or 100 such layers, such hidden layers, then basically the network that we will get will be basically a deep network. And whatever learning we are going to do using such network is termed as a deep learning. So now if you see just a quick look over some, let's say, stats here in terms of the how many number of neurons are there and how many number of learnable parameters are there. So in this first particular example, you can see we have input layer, hidden layer, output layer. Suppose if you have to find out how many number of neurons are there in this particular example, the left side. So input layer is not the neurons, those are input values. So hidden layers, basically we have 4 neurons. Output layer, we have 2 neurons. So how many number of neurons we have? Basically 4 in the hidden layer plus 2 in the output layer. So we have 6 neurons. How many number of learnable parameters we have? How to compute the number of learnable parameters? So if you see, if we have 1 neuron anywhere, then it is how many number of parameters will be associated with 1 neuron. That is going to be dependent upon how many number of elements we have in its previous layer. So suppose if you take a neuron in the hidden layer, then in any neuron in the hidden layer is connected with the 3 inputs. It means that it should have 3 W also. It means it is going to have 3 learnable parameters. So now each hidden neuron is going to have 3 learnable parameters. So it means 3 into 4 is going to be 12. So 12 learnable parameters in the hidden layer itself. Similarly, if you see in the output layer, so one neuron in the output layer is connected with the 4 neurons in the hidden layer. It means there will be 4 learnable parameters. So, and then we have 2 such neurons in the output layer. So 4 into 2 is going to be 8. So 12 plus 8, we are going to have basically 20. So we are going to have 20 learnable parameters, that is W. But we are going to have the bias terms also. And how many bias terms? For each of the neuron, we are going to have 1 bias term. And if you see the total number of neurons, we have 6 number of neurons, then we are going to have 6 bias terms. So 20 weights from the W plus 6 biases is going to be total 26 learnable parameters. Similarly, it can be computed for the second example also. For second example, how many number of neurons? 4 in the hidden layer 1, 4 in the hidden layer 2, 1 in the output layer. So 4 plus 4 plus 1, 9. How many number of parameters? So again, in the hidden layer 1, it is going to be basically 3 into 4. Why 3? Why 3 into 4 here? Because 4 neurons in the hidden layer and each are connected with 3 input. So 3 into 4. Plus in hidden layer 2, 4 into 4, because each of the hidden layer 2 neuron is connected with all these hidden layer 1 neurons. So 4 into 4. Plus 4 into 1 for this output layer, because this is connected with the 4, plus the bias terms. And after adding in all these things, we will get the 41 number of learnable parameters in this particular example. Okay, so now one question comes that if we are saying that we can have a deep model like this, where we can have more and more number of hidden neurons as well as more and more number of such layers, then what is the basically impact of this, or what this is going to do ultimately? So now if you see here what it is going to do basically, if we have more and more number of neurons, fine. What is a neuron? Neuron is nothing but this is just a small computational unit which is going to take some input. It will have some parameters. It will multiply. It will have a bias term. It will add whatever output it is getting. It will apply a non-linear function on that, which is called the activation function. And whatever output it will get, ultimately it will be passed to the next layer. So neuron is nothing but a very tiny, you can say, computational unit, which is taking the input from the previous layer, doing some computation, just producing some output, which is passed to the next layer. But now what impact it is going to do? So suppose if we are going to have more and more number of hidden neurons, then actually we are introducing more and more non-linearity into the network. What is the meaning of non-linearity? Non-linearity means basically it is transforming the data in a non-linear fashion. But where is that non-linearity? That non-linearity in this particular neural network, or in let's say deep neural network, non-linearity is actually going to exist in the activation function. Even you can recall here that we just discussed before. So this sign of this is going to introduce a non-linearity. Suppose your output is getting 5, but ultimately it will output just 1. Even your output is 6, it will output 1. That is non-linearity, means mapping of some input to the output in a non-linear fashion. So now here if you see, yeah. So what is going to happen basically, if you see, if you have only 3 hidden neurons, then if you see this boundary is not going to be very much overfitted, or basically this even some examples that is not going to be properly classified, because we don't have that much non-linearity in our deep neural network, in our neural network. But if we increase the number of hidden neurons, then actually we will increase the non-linearity, or basically the capacity of our neural network. And if you increase the non-linearity nature of the deep neural network, or basically the capacity of your neural network, then it is going to it will be able to model even some complex distribution which is not linear into the scenario. So even suppose here you can see the last one, if we have 20 hidden neurons, in fact you can see this is complete overfitting, means all red ones are getting classified into the red one. And the shape of this, if you see, the boundaries that we are getting, this classes boundaries that you are getting is completely non-linear, because actually we have a lot of neurons in our network. It means we have more and more non-linearity capacity in our network, then it can learn the non-linear data behavior in more efficient way. So that's how actually this deep neural network is basically able to work. If you see nowadays, deep learning has become kind of a very, let's say, popular thing. Why it has become very popular? Because in real scenario problem, or in complex problems, the data is completely non-linear, and the normal classifiers are not able to handle such data. So that's why, yeah. But if you have a huge amount of data, even a very complex data, and if you have a very deep network, here I'm just showing 20 hidden neurons, but actually if you see the number of neurons that nowadays people are using, even the lakhs number of neurons that people are using in the network. So suppose if you have 1 lakh number of hidden neurons, then how much complex data even it can basically learn the decision boundary for that. So again, pros and cons, flexible and journal function, and some downsides like hard to analyze theoretically. That's what is one of the things, because if you have a lot of layers, then how to analyze that, why it is working and what is happening inside the network. And that's what is one of the, let's say, important aspect that people are looking for the network visualization. So now coming to this neural network that we discussed, now I am a little bit moving towards the images that can we use this deep neural network for images. Suppose, just for example, let's suppose if we have this as an input image, let's say this is a cat. Now I want to learn a classifier, let's say a neural network classifier I want to learn for the classification. Is it possible to use this image as the input to this network? That is you can see a neural network at the right side. How to use this image as the input to the neural network? So obviously there could be the let's say different techniques to use. There's just one example that, okay, because image is a two-dimensional data, but if you see the input that is required for the neural network is basically one-dimensional, then we cannot directly use this two-dimensional image as the input to the neural network. Then one strategy could be, okay, let's why not to just stretch this particular image into a just one column vector. It means that taking the first row, taking second row, but appending into the first row, or basically you just stretch it into a one vector. This image, if you just take just hold the top and left corner as well as right and bottom corner and just stretch it out into a single column vector, and then it like this actually we can use as the input to this neural network. But what do you think? Is it a good idea to modify our input from two dimension to one dimension to be used by the neural network? Obviously, this could be one of the technique, but this is going to lead to some major problems. And what could be those major problems? One is the high dimensionality. What is the meaning of high dimensionality? So suppose if you have, let's say, one image, let's say your image dimension is 256 cross 256. If even if you are stretching it out into a single column vector, how many number of values will be there? That is 256 into 256. It means that if in your input you have 256 into 256 number of values, then in your hidden layer also you should have even more than that number of neurons. It means that the number of neurons that we are going to have in our network is going to grow very fast. Then actually it is going to lead to the complexity problem. And second important thing, see, as a human being, if we are able to see this image and we can say that this is a cat, on what basis we are, as a human being, we are able to say that this is a cat? Because due to the local pixel relationship in the two dimension. If suppose if you are saying that this is I, why on what basis we are able to see this is I? Just for example, if I take this particular picture and if I just strip it out into a single column vector, then and if I just give it to you as a human being, can you identify this is a cat from just a single vector? Obviously that is not process. Why? Because we are going to lose the local relationship between the pixels, and that is going to basically restrict the performance even we are adopting such type of techniques. Then what could be the solution? The solution is going to be another a variant of artificial neural network is very commonly used in for image related problem that is called the convolutional neural network. Now, this convolutional what is this convolutional neural network? If you see convolutional neural network, basically also termed as CNN or sometimes convolute or deep convolutional neural network. So convolutional neural network is multi-layer neural network, but with added some property. And what are those properties? It is allowing the local connectivity as well as it is allowing the weight sharing. Now let's have a look. What is the meaning of local connectivity? So now you can recall when we had let's say the discussion over neural network, then we just discussed that any neuron is going to be connected with all the neurons in its previous layer, and that is called the global connectivity. That is depicted here in this particular diagram here in the left side. You can see in global connectivity the number of inputs here, let's say number of neurons are here in the input is 7 and number of hidden is 3 here. Then how many number of parameters we have, let's say in the global connectivity. So as we discussed earlier, the parameters we can compute how this if you take any neuron in the hidden input, how many are in the let's say how many are there in the input, that is 1 2 3 4 5 6 7. So 7 for one neuron and we have 3 such neurons, then 7 into 3 is going to be 21. That is without bias. If you add bias, then it will become 24. But in local connectivity, what is going to happen, any neuron in the hidden unit in the hidden layer is not going to be connected with all the neurons in its previous layer. Rather, it is going to be connected only with a few neurons which is in its close proximity in terms of its spatial location. It means that which is going to be spatially in the similar region and it is very close to that particular let's say neuron, and we are not going to use connect with all the neurons in its previous layer. We will only connect to few neurons. So just for example, here it is connected with 3 neurons in its previous layer. Then in this particular example, suppose if we find out the number of parameters, the number of parameters are going to be only 3 into 3, which is going to be 9. So now in first one there was 1 parameter, but in the second one we are going to have only 9 parameters. And what is the weight sharing? So weight sharing, even if you recall, let's say we for each of the connection we have the independent weights that is depicted in the left side here. But in weight sharing mode, suppose if for one neuron, if the weight is W1, W2, W3 for these 3 connections, then the same weight we can use for the another neuron also. That is W1, W2, W3 for the next neuron also. The same weight we can use for the third neuron also. That is W1, W2, W3. Why this weight sharing will work, that we will see shortly. But after doing this weight sharing, now if you see how many number of parameters we are going to have. So in this particular example, without weight sharing, we are going to have the number of parameters 9, but with weight sharing, we are going to have number of parameters as 3. So now basically these two concepts, that is weight sharing and local connectivity, is going to allow to develop the type of a neural network which is called the convolutional neural network, which can take image directly as the input and it can process directly in 2 dimensions instead of stretching it out into 1 dimension. And basically it is going to have a lot of convolutional layer and a lot of non-linearity layer, which is the reloose here, and some pooling layer to do the downsampling. And then fully connected FC means fully connected means a normal this neural network layer. And then ultimately it is going to produce the class score. So now question comes that then what are the layers here? Input layer, convolutional layer, non-linearity layer, pooling layer, fully connected layer, classification layer. So now let's have a quick look over this, that what is this convolutional layer? So convolutional layer is nothing but this is derived from the concept of filtering. So now what can be done here, suppose if this is our input, now we will take the input directly into the 2 dimension even with more than 1 number of channels. So for example, suppose if you have a color image, then we can have the 3 images, we can have 3 basically frames there, and basically 3 color channels, that is red, green and blue. So suppose if our spatial dimension is 32 cross 32, then 32 cross 32 cross 3 is going to be basically, let's say, the input dimension here. Let's say there is an input color image with 32 cross 32 is as the spatial dimension and 3 as the number of channels. So now what is going to happen here in the convolutional layer? We are going to have a kernel. Now our kernel is also going to be in 2 dimension basically, and with more than 1 number of channels. And how many number of channels, that is going to be decided based on the number of channels in my input. Suppose if in my input, if I have 3 number of channels, then in my kernel also I am going to have 3 channels. And what will be the spatial dimension of the kernel? That can be 3 cross 3 or 5 cross 5 or 7 cross 7. So generally, if you see even in the filtering concept also, generally the kernel size is in the odd term. Why it is in the odd term? Because if it is in odd term, then it can retain the symmetry across the center. So if it is a 3 cross 3, then if you take the center, then it will retain the symmetry. If it is 5 cross 5, still if you take the center, it will retain the symmetry. So that's why generally the filter dimension is treated as basically the odd number. So now again, if you see here, just for example here, suppose if my filter dimension is 5 cross 5, that is a spatial dimension, but how many number of channels will be there in my filter? That is going to be governed that by the fact that how many number of channels I have in my input. So here you can see in my input I have 3 number of channels. So in my filter also I'm going to have 3 number of channels. So now what is the next that we are going to do? Now next we will take this filter and now we will do the convolution across each of the pixels are basically across each of the spatial location in my input. So here you can see. So now what we are going to do, suppose if you take this one as the middle one, so basically we are going to just align with the middle pixel, let's say with each of the pixel one by one, and then we are going to basically just do the basically convolution. And what is the meaning of convolution here? So convolution is like, this is not the exact convolution that is derived from the signal processing perspective. This convolution is basically a simple dot product that is generally used here. So so if someone is from signal processing perspective, you don't get confused with this convolution. So the convolution that is used in convolution neural network is actually the correlation, not convolution exactly, that is derived from the signal processing. So basically this is going to just do the dot product, and dot product will happen across each of the channel. Means the first channel of the filter is going to do the dot product with the first channel of the input. The second channel of the filter is going to do the cross product, dot product with the second channel of the input. The third channel of the filter is going to do the dot product with the third channel of the input. And ultimately it is going to produce a single value by adding all these terms. So now after doing this convolution, we are going to produce a single value here. And if you see in this particular example, how many number of operations are involved here. So basically in my filter, I have 5 into 5 into 3. So 75 values I have in my filter. Filter means what? I have 75 number of parameters. Fine. And out of that, 25 parameters in the first channel, 25 parameters in the second channel, 25 parameters in the third channel. These parameters means these are learnable parameters. Somehow we are initialized with these parameters, but later on we will change the values of these parameters based on some strategy which is called the gradient descent. Basically, that is the optimization techniques that is used in deep learning. So now, based on doing this convolution at one location, we will get one value. Similarly, and in fact, here you can see, so this diagram is giving you a very nice picture that how we are going to do. So in this, you can see this is for a 3x3x3 filter. This filter, you can think like that. If you just do the dot product with by taking the input value of the same dimension and then just shifting in the right direction, then again doing, then shifting again, doing, then going down, and just repeating this process for all the spatial location. So suppose if you just do this, if you repeat this for all the spatial location, then actually we are going to generate one channel in my output, right? Because for corresponding to let's say one center pixel and having its neighbors, we are going to produce one value in my output channel. And if you just repeat this process for all the spatial location, then actually we are going to produce the whole channel here. Yeah. But what is the depth of this channel? How many number of channels we are going to produce here? Then actually we are going to produce only one channel here. See, we started with the 3 channels in my input, but now I am ending with only one channel. So now the number of channel in my output can be increased by having another filter. What we can do now, we can have one more filter which is also having the same dimension, like 5 plus 5 plus 3, but values will be different. Those 75 values in the filter will be different. And then again, if I repeat the same process, then I will end up with another channel. Similarly, suppose if I am keep doing if I consider one more such filter, then again I am going to get the another channel. Like this, suppose if I have 96 such filters, just for example, 96 such filter, and each filter has a dimension 5 into 5 into 3, where 5 into 5 is a spatial dimension and 3 is the number of channel, then each filter is going to produce one channel. And if we are having 96 such filters, then it is going to produce 96 channels in my output. So, and yeah, because I have not performed any padding here, then the spatial dimension is going to reduce here. So original spatial dimension is 32 cross 32, but now here it is 28 cross 28, because we are not using padding. And obviously if we are not using padding, then we cannot consider this top let's say either from top or from bottom or from left and right, this 2 rows or 2 columns we cannot consider, because then we will not get the sufficient values to do the dot product. So that's why this dimension got decreased to 28 cross 28. So now on top of this output, we can have the activation functions, we can have the non-linearity, we can have some other layer, and in fact we can have another convolution layer also for that. And in fact, this is just visualization here that how this is working. So if you see, these are 3 if you see, this is the first one is corresponding to red channel, then green channel, blue channel, and similarly we have 3 channels in our filter also. You can see 3 1, and then in order to produce in the output the first value, which is -3 here, you can see in output volume the first value -3. How this -3 is computed? So what is going to happen? This filter is going to be multiplied a dot product with these neighboring values, which is highlighted. Red one, second channel with the red one, third channel with the blue one, doing this dot product, and then adding the bias term here. If you see, bias term is 1. After adding this bias term, basically we are going to get this output -3. How we'll get output -1 here? Basically we are going to shift by some position. By how many position we are shifting, that is called basically the stride. The means by how many number of position you are shifting your window, and again repeating the same process, then we will produce the next value. Similarly, if we have another filter, for another filter we can produce another channel here. You can see the second channel values 142, -145, 315, 313. This is produced from the filter W1. The first one is produced from the filter W0. So now whatever output we got, let's say this is my input as a color image, 32 cross 32 cross 3. I have 96 filters, each filter dimension 5 into 5 into 3. And then my output dimension will be 28 cross 28 cross 96. Why 96? Because 96 such filters are there. What is the dimension of the filter? 5 cross 5 cross 3. Why 3 channels in the filter? Because 3 channels we have in my input. Now whatever output I have got it here, that is 28 cross 96, that can be also used as the input for any other layer. In fact, another layer can be another convolutional layer itself. Suppose now I want to apply one more convolution layer. Then in another convolution layer, if I'm going to have a filter, then that filter should have 96 channels. Why that filter should have 96 channels? Because in my input here, now my input is this 96 channel activation map. So my input has a 96 channel, so filters would also have 96 channels here. And again, we are going to repeat the same process that we did for in earlier case. And one filter with the dimension 5 cross 5 cross 96 is going to give us only one channel in the output. Again, suppose if you want 128 channels, suppose if we have 128 such filters having the dimension 5 into 5 into 96, then actually we are going to produce the output having 128 channels. So that's how actually the number of channels we are going to increase. So now what is going to happen here? So now if you see in a typical convolutional layer, let's say if you are applying for a classification problem. Suppose if you have 10 classes, or let's say suppose if you have C number of classes. Now this input, any input if you take, corresponding to that input, your convolutional neural network is going to produce C number of basically class scores. And how it is going to do? So basically, it will take the input, and over the layers, over these convolutional layers and other layers, over the time or over the layers, it is going to reduce the spatial dimension. So generally, if you see from 32, it became 28, then it became 24. Next time, it will be again decreased. And the number of channels, it will first increase the number of channels, let's say from 3 to 96, then 128. Then after that, we can go for 512, then 1024. Generally, people prefer number of channels as the power of 2, just for the optimization purpose. That in computer science, if you see, if things are in the power of 2, then it is efficient for processing, because most of the time, if you see the number of buses in the computers are, let's say the memory utilization are basically somehow related to the power of 2. So over the time, what it is going to do, it will decrease the spatial dimension, but at the same time, it will increase the number of channels, and then again, it will decrease the number of channels. And ultimately, in the final output, the spatial dimension will become 1, and the number of channel will become C. Then what will happen? Just think like this: 32 cross 30, 32 cross 30, 32 cross 32 cross 3 is the input. 32 cross 32 is the spatial dimension is decreasing over the time. Number of channels is increasing over the time. And after some time, the spatial dimension will become 1 cross 1, and the number of channels will become C. And then at that particular time, you will get your class scores. And then C values that you will get basically will become the class score for your C number of classes. So now if you see any convolutional neural network, the two properties that we talked about, local connectivity, if you see, suppose if you are just doing a convolution here, you are taking only some, let's say 5 cross 5 cross 3 values in the input, but you are producing one output. So this is the local connectivity. It means in order to get out one value in your output, you are not considering all the input. You are only considering its local region. So that's how it is basically considering the local connectivity. What is the weight sharing? The same filter, you are just striding over the whole spatial region, and you are just doing the computation, and you are producing one channel. It means that in order to produce one channel in the output, you are using the same kernel just by doing the sliding here. So that's how this is also ensuring the weight sharing. And in fact, other properties, it can handle the multiple input channels. You can have 80 number of channels in the input, then corresponding to that, you have that number of channels in your kernel also. In fact, you can handle any number of output channels. Suppose if you want k number of output channels, then you use k number of filters, then it will produce k number of output channels. Closer look at a spatial dimension that I will skip here because this is not that much difficult task here. This is just simply, if you are just doing this filtering, I think most of you should be aware with the basic image processing concepts, the filtering concepts. There you can figure out that if you have, let's say, one filter, and for that filter, if you want to retain the dimension, then what should be the amount of basically padding that you should involve. So amount of padding basically can be figured out very easily. So just for example here, this is if f is equals to 3, it means that if you have 3 cross 3 filter, then there should be a padding by 1. Padding means what? So padding means just adding some values at the boundary, means appending some values. If filter size is 5 and you want to retain the original dimension, then padding should be by 2. If filter dimension is 7 and you want to retain the original dimension, then padding should be 3. So yeah, so now here you can see that suppose if my input dimension is 32 cross 3, and if I have 5 cross 5 filters and 10 such filters with stride 1, stride means what? By how much amount we are shifting after doing the one convolution, and padding is 2, then what should be the output volume size? So output volume size can be computed easily. How? What is the original dimension? That is 32. If you are applying the padding, then generally padding is, if you are applying in the top, then in bottom also the same padding amount is there. Then 32 plus 2 times padding amount minus what is the kernel size? Kernel size is 5. So 32 plus 2 into 2 minus 5 divided by what is the stride amount? The stride is 1, so divided by 1 plus 1. So that is going to give us the output basically dimension. So what is the spatial dimension in the output? So it is going to be 32. So 32 into 32. But how many number of channels in the output? So we know that number of channels in the output is equivalent the number of filters, and we have 10 filters. If you have 10 filters, each filter is going to give us one channel in the output, then the number of channel in your output is going to be 10. It means that the dimension of the output volume will be 32 into 32 into 10. How many number of parameters involved here? So obviously parameters we can compute from our filter. We have the filter. What is the dimension of the filter? 5 cross 5. How many number of channels in the filter? That is equal to the number of channels in the input. In the input, number of channel is 3. It means in the filter also number of channel is 3. Then 5 into 5 into 3, that many number of values, that many number of parameters. If you are using the bias also, then plus 1, then 76 parameters. And how many such filters? Suppose if we are going to have 10 such filters, then 76 parameters for one filter. And suppose if we have 10 such filters, then the total number of parameters will be 760. This is just summarizing the same thing, that suppose if these are the input dimension, and let's say this is the kernel property, then what should be the output dimension? Yeah, one important thing, that what this convolution is doing. So convolution is basically very heavily, if you say convolution neural network is very heavily dependent upon, or basically driven from the filtering concept of image processing. If you see in image processing, what a filter is doing, basically, suppose if you want to detect the age, what you will do, then you will design a filter, let's say some Sobel filter, or some let's say other filter, private filter. And what those filters are doing, those filters itself are having the edge information, are basically mimicking the edge information. And if you just do the convolution with your input, then the same type of information it is looking in the image. And when it is looking the same type of information in the image, and if such information is found at some place, then in the output their higher values will be basically produced for with respect to those reasons. Similarly, here also, suppose if we are going to have just for example some, let's say some number of filters here, some number of kernels, then each kernel is going to basically learn some visual characteristic with respect to our input. So for example, here you can see, let's say this particular kernel might be looking for something which is going to be, let's say, related to this such particular scenario of a car, just for example. So such type of outputs we are going to produce here, and then on top of those outputs, we are going to have another layers, another convolutional layer, other layers that is going to again transform those images. Sometimes we might have to drastically decrease the spatial dimension. Then there are some pooling layers that is generally used. So pooling layer is going to decrease the dimensionality, for example, here from 224 cross 224 to 112 cross 112. Max pooling is very common and very heavily used. Regarding other layers, fully connected layers is nothing but the simple neural network layer that even we have seen in normal artificial neural network. And classifiers, we have already discussed the SVM classifier, softmax classifier. Non-linearity layer, yeah, I'm not going into the detail, but these are some common non-linearity layer. If someone is interested, you can have a look.
Sir, can you hear me?
Yeah, Vishal.
Sir, maybe we can
I think it is done now.
Okay.
Yeah, so basically if you see what is the journey from machine learning to deep learning, that's what we looked upon. If you see, the deep learning is also basically derived from the basic machine learning concept, basic linear classifier concept. If you see, if either you take linear classifier or you take SVM classifier or you take any classifier, even in neural network also we saw that all the classifiers are actually doing W dot X B. And that W dot X plus B is nothing but the W are the parameters, X is the input, B is some bias term, and we are computing those values. And ultimately, we are just doing some processing on top of those values in order to get, let's say, something. And some classifiers are there, for example, SVM, softmax. So softmax, we saw that why it is better than SVM classifiers in deep learning scenario, because it is always trying to go towards the 100% classification probability. It will strive for that. And in deep learning also, if you see, deep learning is nothing but you are going to have more and more number of layers here. If it is normal data, that is one-dimensional data, then you can have deep artificial neural network. But if you are having images, then you can basically go for the convolutional neural network. In convolutional neural network also, we can have many number of corner layers, we can have many number of pooling layers, many number of activation functions. Ultimately, if you increase more and more number of layers, then we are going to have a deeper and deeper network. And what is going to happen if you are having deeper and deeper networks, then basically you are going to have more and more processing units, you are going to have more and more non-linearity into your network. Then actually it can be used in order to learn the characteristic of even a complex data set or even a huge data set. So that's what has happened so far. And now if you see, in image processing and other areas, this image-based inputs where image or videos are used, this image processing has this convolutional neural network has been used extensively. And the first convolutional neural network that came actually in 2012, basically, that owned the ImageNet classification challenge, which is very popular challenge. And after that, a lot of progress has been happened in this convolutional neural network field. So with this, I'm going to end. So these are a few of my research areas. I'm not going deeper here, but some of the problems which is related to images or videos that we are trying to solve here, which is related to some, let's say, medical image analysis, as well as face-related issues like recognition, microexpression, anti-spoofing. In fact, nowadays there is one progress, a lot of work is happening that is called the generative adversarial network, where we can transform one input in some other output form. Just for example, here you can see sketch is transformed into the actual image form, or thermal image is transformed into the visual form. Some other works that we are doing as the core deep learning work, where we are also working on the optimization problems. For example, diffgrad is one of the optimization techniques. Activation functions also we have looked upon that can give the better training for the network, and some other losses, even improvement of the cross-entropy loss like hard mining loss. So these are some works that we are doing in this deep learning area. So with this, I'm going to end this particular session. So again, just a quick look. We started from very basic nearest neighbor classifier, and ultimately we came up to the convolutional neural network, and that's what is the journey from machine learning to deep learning. So now I would be happy to take any questions or any doubts that anyone has.
Thank you so much, sir. This was really helpful, and the entire session was very interesting and very insightful. So I would request all the participants, if you have any questions, then if you can raise your hands, and if you want, please raise your hands. Then I'll call out your name if